lesson today, we're going to be discussing sinusoidal curves, which is just another word of saying sine curves and cosine curves. We'll quickly look at some of their key characteristics and discover what happens when we perform transformations on them. We'll also learn how to graph our own sinusoidal functions with transformations using an easy step-by-step process. But let's start with our original sine curve. We should make sure we're familiar with the look of this curve. It has key transition points every 90 degrees, starting at 0, 90, 180, 270, and 360. And notice how its cycle will start at the middle. We call that middle dotted or dashed line there the horizontal axis. It acts as the middle of our curve from the top to the bottom. If the maximum of our curve is at 1 and the minimum is at -1, the horizontal axis will go through y equals 0. Our sine curve also has an amplitude of 1, a period of 360 degrees, and it continues forever in both directions. We say that this curve is periodic, and another way to say this type of curve, or a wave-like curve, is a sinusoidal curve. The cosine curve looks very similar. In fact, it's the exact same shape as the sine curve. It has the same amplitude, the same period. The only difference is that the cosine curve has a phase shift that is left 90 degrees compared to the sine curve. Essentially, that means that sine curves and cosine curves are the exact same curve, except it looks like a cosine curve starts 90 degrees sooner than a sine curve does. If a sine curve has its starting value at 0, which is in the middle of the curve structure, we say that a cosine starting point starts at 1 and is at the top of the curve structure. It then makes its way to its other transition points, just like the sine curve does, every 90 degrees, except it starts at the top. So the next transition point is in the middle, then the bottom, back to the middle, and then finally finishes and starts its new cycle at the top. For the beginning of this lesson, we're just going to focus on sine curves, because sine curves and cosine curves are pretty much identical other than a difference in shift. We'll focus on sine curves, and later on we'll be able to graph both sine and cosine curves. Just like other functions we've seen so far in this unit, whether it be quadratic functions, exponential functions, or any other types of functions, they can be transformed. We can reflect them, we can stretch them or compress them, and we can translate them up, down, left, and right. Sinusoidal functions work the same way. And if you look on the left of the screen, you'll see that I have sine x written as an equation, but I also have an equation that uses sine in a function that has a bunch of different transformations, and we've used letters to represent these transformations. The a out front can represent different stretches and compressions that happen vertically, as well as any reflections that might happen over the x-axis. The k value inside the function represents horizontal stretches and compressions, or any reflections over the y-axis. The d value represents translations left and right, and the c value represents translations up and down. We also want to keep in mind that any transformations that are related to x values are always backwards to what we think they should be when we look at the equation. I've also included an equation for our horizontal axis. You'll also notice on the left that I have 4 different sliders that I'm using with Desmos that can slide the values of a, k, d, and c to different values. And we're going to see what happens when we change those sliders. Right now we're starting with the a value being 1, or really without there being any stretch or compression, as well as the k value equaling 1, and no translations up, down, left, or right. A lot of these transformations will happen just as we suspect they might. If we want to move the graph up or down, we know that we need to adjust this c value that's here. So if we move the c value, let's say to a positive number 1, our blue graph, which represents the transformed graph, has moved up 1 unit. All of our key points have also moved up 1 unit as well. Also note that the horizontal axis has also moved up 1 unit. The same thing would happen if we moved the c value down, that our whole graph would move down. Our d value is going to react in the same way. It's going to move our graph left or right. But remember, it's backwards to what we think. So in our equation, when we have a negative d value, it actually means the d value is positive because the equation originally had a minus sign. When the d value is positive, we're going to be moving our curve to the right, which we can see when we move our d value to positive values. When we use d values that are negative, our curve shifts to the left. Those two are the easy ones. But what happens when we adjust the a and the k values? With other functions, when we adjusted the a value, it was a vertical stretch or a vertical compression. When the a value was greater than 1, it was a vertical stretch. So if we increase the a value for us, notice how our curve stretches up vertically. We have these main points here that are staying on the x-axis. We call them invariant points because they don't move when we perform our transformation. But all the other points are moving. When we make the a value less than 1, it compresses down vertically. So we can see that we're squishing our curve rather than stretching it. And just like before, if we made our a value negative, it causes a reflection. This is what the reflection of an a value of negative 1 looks like. It's almost like a double helix for a DNA molecule. Finally, we have the k value. The k value is going to compress or stretch things horizontally. Remembering that that k value also has backwards thinking. So when the k value increases, we should have a compression. And that's exactly what happens. Our curve compresses on itself horizontally, so as if we're squishing it from the sides. A big change that's happening here is that our period is no longer 360 degrees. That changes depending on what the k value is. And in this case, we've now created a period that's 144 degrees when the k value is 2.5. If our k value got smaller than 1, we've stretched this out. So much so that we can't even see it on our graph. So I'll have to zoom out here so that we can see an entire cycle's worth of curve. There's the start, and there's the finish. 1,440 degrees for one cycle. That's with a k value of 0.25. So we've seen what these transformations can do. But knowing we have a periodic function that has an amplitude and that has a horizontal axis and that has a certain length for its period, how do those things change depending on what our a, k, d, and c values are? Well, we've seen that if we adjust the a value, it vertically stretches our curve. Notice how the maximum point has now gone up to 1.5 and the minimum point has gone down to negative 1.5 when the a value is 1.5. The amplitude, therefore, is the distance between the top and the bottom, but cut in half, or the distance from the maximum to the middle, or the minimum to the middle. In both these cases, it's 1.5, which is the a value. So an easy way to remember this is the a value is the amplitude. Another easy one to remember is the horizontal axis. It moves when our parabola moves up or down. So if I move the whole parabola up 1 full unit, notice how the horizontal axis also moved up 1 full unit. It's now at y equals 1. So an easy way to remember this is that our horizontal axis is just equal to the same value for c. Whatever c is, that's where our horizontal axis will be. And that's easy to see. A trickier one to compute is to figure out how long one cycle lasts, or the period. Right now, our period for a standard parabola that hasn't been transformed is 360 degrees. Let's move our k value from 1 to 2. We already saw that this will horizontally compress our curve. And if we just focus on where our curve starts one cycle and ends the cycle, which is the start of a new cycle, we can see that that takes 180 degrees. It was 360 degrees, but now it's 180 degrees. How did we get to that number? Well, we can take 360 degrees, our original period, and divide it by the k value, 2. 360 divided by 2 is 180 degrees. This will always work. If we adjust our k value to be 3, well, that means that our period should now last 360 divided by 3, which is 120 degrees. It works the other way as well. If our k value is 1/2, and I zoom out, we'll see that our period length should be 360 divided by 1/2, which is the same thing as multiplying by 2, or 720 degrees. The 360 now only marks 1/2 of the cycle. The last little bit of information we can glean from the k value is how far it is to each transition point. Remember, our original sine function started at 0, 0, which was in the middle, and then its next transition point happened at the top of the curve, when it reached 1. This is happening at 180 degrees when the k value is equal to 1/2. It then made its way back down to the middle, met at the bottom, and then back to the middle. That's one full cycle of a sine curve. Notice how each one is occurring every 180 degrees, or a quarter of the length of the period. If we take the period length and divide it by 4, that's going to give us how far it is to each transition point. So when we move our k value back to being 2, if our period is 180 degrees, then every transition point is going to be a quarter of that amount, or 180 divided by 4 is 45. So every 45 degrees, we're going to have a change in direction for our curve. All of these values for a, k, d, and c will be the same for cosine curves as well. It's the same shape, just with a different shift. One final point of note is a little bit on the terminology. When we translate sinusoidal curves left and right, we don't just call them shifts, we call them phase shifts. So if you hear that term, that's what we mean. We translated to the left or to the right a certain phase shift amount. Alright, enough of talking about this, let's actually graph some of these curves ourselves. The first graph we're going to try to create is y equals 3 times sine x plus 1. We can see that we have an a value here of 3, and we're going to be shifting up 1 unit. There aren't any other transformations that are here. To graph sine or cosine curves, we like to follow a step-by-step procedure that'll be the same each time, and it makes it really easy to graph it. In fact, we don't even need to graph using an RST chart if that's something that you've used to graph other functions in the past. This procedure works out pretty easily once you know how to do it. The first thing we want to find is where is our horizontal axis going to go? Remember, we can see the horizontal axis by looking at the c value. Whatever the c value is, that's where our horizontal axis will be. So our c value here is positive 1. That means our horizontal axis will be at positive 1. So I'm going to draw a dashed line here to represent the horizontal axis of our curve. And I'm also going to write the equation of this horizontal axis on the end. Y equals 1. I'll also put a little 1 here to signify that this is going to be 1 unit in length. The next piece of information we need to figure out is where our vertical key points are going to be. Meaning, what is the max, what is the min, and where is the middle going to be? We already know the middle is at 1, and because we know the amplitude is 3, our max is going to be 3 above the middle, and our min is going to be 3 below the middle. So our max is just equal to the c value, which is the horizontal axis, plus the amplitude value, and the minimum is just going to be the c value minus the amplitude value. In our case, we have 1 plus 3 will be the max, which is 4, and 1 minus 3 will be the min, which is negative 2. I'm just going to extend this line here so that I can make -2 be one of the values. It looks like when I originally drew my scale, I didn't really consider where my max and min would be. So I'm going to make this small adjustment on my curve, or on my graph. And you can do the same thing if you realize that you've incorrectly drawn your scale, and you may have to. So I'm going to move this down slightly. So now it looks like we have 4 units up to 4. This is only 1 unit, and this -2 is 2 units down from our original x-axis. Okay, so now that we know where the top of the curve will be, and where the bottom of the curve will be, and where the middle of the curve will be, all the vertical key points have been achieved. Now let's think horizontally. What we need to do first horizontally is figure out what is going to be the length of our period. Remember, the period value is found by calculating 360 degrees divided by our k value. If we look at our equation, there's no k value that's right next to that x. So the k value is actually 1. 360 divided by 1, 360 degrees. From this period, we want to figure out how often are we going to have transition points. Remembering that transition points happen every quarter of a period, this is equal to 360, which was our period, divided by 4. 360 divided by 4, 90 degrees, which is the same as our original sine curve. And because we haven't adjusted horizontally compressed or horizontally stretched, this should be the same. Once we know how often we're going to have transition points, we now draw our scale on the x-axis. We are going to put a key point every transition point. So I'm going to have one at 90, I'm going to have one at 180, 90 later is 270, and then 90 after that is 360. Notice how I put the scale on the x-axis and not on the horizontal axis. We should rarely write anything on the horizontal axis because all our scales should go on the original x-axis and y-axis. Now that our scales have been completed, our last step is to now draw the curve. Remember, our sine curve has 5 transition points, and the first transition point started in the middle. Since there wasn't a phase shift left or right, our first transition point will happen when x equals 0. And it also happens in the middle of where our curve is, which is on the horizontal axis. So we're going to put a dot right here. 1 unit up from the x-axis, and at 0. Our next transition point for a sine curve moves it all the way to its maximum. The maximum value is 4, so at 90 degrees, 1 transition later, and at the maximum value of 4, we're going to put another dot. The third transition point moves it back down to the middle, 90 degrees later, so 180. And then 90 degrees later, we're at the minimum, or the bottom. And 90 degrees after that, we're back at the middle, starting a new cycle and ending the first one. Once you have your 5 transition points labeled, the last thing to do is to draw the curve. And this takes the most practice. Drawing sinusoidal curves is challenging. It's not the easiest thing to do in the world. And attempting to do it on a computer is a bit tougher as well. But you're going to do your best. Ideally, we want to make sure that we don't have straight lines. So when we draw our curve up to the point, make sure that it rounds itself near the top, almost like a parabola. And when you come through this middle point, you're going to curve it the other way around, just like it's now a right side up parabola. And we want to extend it beyond the last point and extend it beyond the first point. It's not the prettiest graph in the world, but it does its job. We're finally just going to write our equation, y equals 3 sine x plus 1, and we're finished. All right, we've got one graph out of the way. Let's try another one. Here, we're asked to graph y equals 5/3 sine of 2/3 x. These fractions look pretty gruesome, but we're going to see with the way we've been graphing that this is actually easy to overcome. To start, we need to figure out where our horizontal axis is. And with no c value, that means our horizontal axis hasn't moved from its original x-axis. I'm still going to draw it on with a dashed line. And I'll make that a different color so it might be easier to see. That's better. And I'm still going to label it. This is the equation y equals 0. Our next step was to figure out where the minimum and maximum is. And we do this by using the amplitude. The amplitude is 5/3. So we're going to be 5/3 units above the horizontal axis and 5/3 units below the horizontal axis. Well, that's easy to draw. Let's say 5/3 is here and negative 5/3 is down here. In fact, you can make this scale as big or small as you want. Maybe I don't want to stretch it out as much, so I'm going to move 5/3 to here, and I'm going to move negative 5/3 to here. It's your scale. You can do whatever you'd like. Just make sure it's about the same distance from the middle to the top and the middle to the bottom. Now we have to calculate our period. And this one's going to be a bit trickier because we do have a k value here. Remembering our period is equal to 360 divided by our k value. And our k value is a fraction 2/3. So this is going to equal 360 divided by 2/3. Knowing our rules for fractions, when we divide by a fraction, it's the same as multiplying by the reciprocal of that fraction. So 360 times 3/2, and 360 times 3/2 is 540. So one cycle is going to last 540 degrees, which is the period. Now the period is nice to know, but it's the transition points that we really need to know. So the transition points happen a quarter of a period, or in our case, 540 divided by 4. 540 divided by 4 is 135 degrees. On our scale on the x-axis, we're going to put 135 degrees for every key point. 135, 270, 405, and 540. If our period was any different, we could just change the numbers and keep the same scale. Again, graphing this is pretty easy. It's just the numbers on the scale that we need to change. Finally, because we have a sine curve, we start in the middle at the original spot, which was right here, move to the top, back down to the middle, then go to the minimum, and then back to the middle, making our 5 transition points. And now you draw your curve as best as you can, and because you're doing this freehand, you can erase it if you'd like, but try to go through the points as best you can and extend beyond. And that's our curve. Finally putting the equation beside it, y equals 5/3 sine 2/3 x. Okay, we're going to graph one final curve. And to give us a little bit more of a challenge, we're going to make it a cosine curve. We're going to graph y equals negative cos of 3x minus 270 plus 2. There's a lot going on here. But to start any question that we need to graph, we always start with the horizontal axis, which is just the c value. In this case, positive 2. So let's put our horizontal axis here at positive 2, and don't forget to label it. Y equals 2. I'm also going to put a 2 right here. Next, figure out the max and the min. We get that from the a value because it's the amplitude. There's a negative there, which means we're going to have a reflection, but the a value itself is 1. So the maximum is going to be 1 unit higher, and the minimum is going to be 1 unit lower than the horizontal axis. Okay, what about our period? We've seen questions like this before, where 3x minus 270, we needed to factor this number that was in front of the x. It's no different now. We still need to rewrite this in a form in which we could properly read the transformations. So let's common factor out this 3 that's in front of the x and see what we end up with as our d value. In this case, we're going to get y equals negative cos bracket 3 And then because it's getting common factored out, we have x minus 270 divided by 3 is 90 plus 2. If you notice there should be some factoring here, make sure you do that step first. We got lucky that it didn't affect us vertically, but it will help us when we need to read the transformations horizontally. The k value we're working with is 3, so our period is going to be 360 divided by 3, which is 120 degrees. And if our transition points happen every quarter of a period, then we're going to have them every 120 divided by 4, or 30 degrees. So let's add that to our scale. 30, 60, 90, 120. 30, 60, 90, 120. Now, we're working with cosine. So cosine, if you remember, doesn't start in the middle. It actually starts at the top of its cycle. So we would normally start right here at the top, which is 3. But there's two other things that are occurring in this graph that we have to be mindful of. The first is that this is being reflected over the x-axis, or reflected vertically, meaning that instead of being at the top to start its cycle and then moving to the middle for its next transition point, we're actually going to flip it so it starts at the bottom and then it moves to the middle for its next transition point. It's the exact opposite pattern. So if it was a reflection and it's a cosine curve, we're going to start at the bottom. But hold on, there's one other thing we have to remember. Here we have a phase shift. 90 degrees, and remember it's backwards thinking, so 90 degrees to the right. So instead of starting at the bottom right when x is 0, we're actually going to start at the bottom when x is 90. We need to phase shift over. Our next point will then move to the middle 30 degrees later, because that's our transition point. So we're going to put a dot here. And it looks like we're going to need to add more to our scale. So we went 90, 120, the next will be 150, 180, and then 210. Let's see if that helps. We start at the bottom, move to the middle, then we graduate to the maximum or the top, back down to the middle, and then we finish up back at the bottom. So when we draw our curve, remember that the bottom, we don't want to go beyond the bottom. This is where we're transitioning back up. So I would start your curve slightly above that dot and curve your way through it, as if you're finishing the parabola, just like this. And then you're going to slide your way through this and again finish your curve so it's back on the upslope. We draw arrows there to say that it continues, and we're going to write our equation. Y equals negative cos, and it's okay if you write the factored form because it's the same. So x, or 3 times x minus 90 and then plus 2. Now one interesting thing of note. Remembering that these curves continue on forever, let's just say we continued this curve back to the y-axis. So I didn't end the curve here, but I just kept doing transition points. Every 30 degrees we're going to write a new transition point following the pattern, but now we're just going to work the pattern backwards. So if it's at the bottom, it's now going to reach the middle, and then 30 degrees later it's going to reach the top, and then 30 degrees later it's going to go back to the middle. And if I continue the curve through that point, up and around here, and then back to the middle, what you can maybe notice is that this curve starts on the y-axis at the middle and then transitions up to the top, just like a sine curve would. I wonder if we can write an equation that would represent this curve as a sine curve rather than representing it as a cosine curve. All we need to figure out is what's the amplitude, which is the same as the amplitude that we had for our cosine curve. That doesn't change. We know that there won't be any phase shift because sine curves always start at the y-axis in the middle and then transition upwards, which is exactly what this one's doing. So the only thing we need to remember is the amplitude, the k value, which was 3, and the horizontal axis, which was 2. We could write an equation for a sine curve that is y equals sine 3x with no phase shift plus 2. And our amplitude is 1, so we don't have to write a number. And it turns out that sine 3x plus 2 is the same as negative cosine of 3 bracket x minus 90 plus 2. They create the same curve. And in a future lesson, we're going to look at how do we write a sine curve if given a cosine curve, and vice versa. But until then, enjoy practicing graphing your sine and cosine, or sinusoidal curves.